Whew. There we go. You started recording. I'm not allowed to swear anymore, so this is good. All right, let's try this. You need your textbook for today, but also you need the new notes package, so I'm going to give you that. Again, we're going to review the test on Monday. Yeah, you got it. Here's the notes. Here's the checklist review booklet.
Where's mine?
Yeah. Yeah. Okay. Here's the notes. Holy! What's going on? And this organ. That's you. That's Is Kyle here with me? Oh, is Kyle there now? Okay, did you get one of each? Yeah, you did? All right. Roby's cleaning up after my Okay. So what I just gave you, I just handed out the 5.1 notes, and I just handed out the Chapter 5 checklist and review booklet. So you're getting that review booklet from day one. Let's look at that review booklet. What are the two major things in that review, under the 5.1 section of the review booklet? What's that first one? It says classify matter into homogeneous mixtures, bracket solutions, and then heterogeneous, bracket mechanical mixtures, and pure compounds and elements. Okay? So that's kind of one of our two goals today. And what's our other goal? Number 2. Identify acids, bases, neutral ionic compounds, and neutral molecular compounds based on diagnostic tests. And what are the two diagnostic tests in brackets? Litmus and conductivity, right? And so, actually, I'm going to be perfectly honest with you. Nothing that we're going to do today is new. It's all review from Science 10. Do you remember doing litmus tests from Science 10? Yup. Do you remember talking about conductivity tests in Science 10? Yup. Do you remember talking about homogeneous and heterogeneous? Yup. So it's all review, basically. That's it. So we're going to really try and quickly cover this review. And then we're going to go in, but we're going to start thinking about how can you write a proper lab report. How can you, not lab report, but how can you write a proper lab procedure? Is that okay? We want to talk about writing a proper lab procedure today, if you were to ever make your own lab procedure. So, we can classify matter into 4 different groups: elements, compounds, mechanical mixtures, and solutions. These first 2, I want you to be specific. They are both pure substances. I'm going to draw some pictures today so that you understand what the heck is going on here. Mechanical mixtures and solutions are both mixtures. A pure substance is something it's like all of the particles that thing is made up of are totally identical. Okay? So let's think of any pure substance. What's the most common pure substance on the planet?
Water.
Water. What does every particle of water look like? It looks like this. It's H2O, right? So would you agree that this thing and this thing, barring any artistry skills or imperfections, you know what I mean? Do they look identical?
Yes.
Yes. Are they composed, is each particle made out of a single type of atom?
No.
Is it all made out of one type of atom here?
No.
No, I don't think so. Is the red thing different from the white thing?
Yeah.
Yes, definitely it is different, right? Okay, so this is what we call a compound. A compound is two or more elements bonded together, but we can still have pure water. Here's a water molecule, here's a water molecule, and they can swim around and they can bump into each other, whatever. It's still pure, Ashley. Yeah, you gotta go, you gotta go. So I want to be very clear, and I want to draw some pictures, and hopefully I can reach this. There you go. I don't need Wim's help. So let's draw a little bit of a diagram so that we can organize our thoughts. Do you have a little bit of room between here and the next thing?
Yes.
Yeah, you got a little bit of room here. So let's draw the organization of matter, the classification of matter that you've been drawing. This is your third year drawing this picture now.
Fourth.
Is it your fourth year? You don't know. You don't know. So matter can be split up into what two different categories? What can matter be split up into? Pure substances and mixtures, right? So on one side, we're going to put pure substances. And on one side, we're going to put mixtures. Pure substances, we define pure substances to be made up of like all the particles in that substance are totally identical to each other. All particles are identical. In a mixture, you're going to have particles that are not identical. You're going to have particles like one's one type of particle, one's another type of particle. So for example, if I ever dissolve anything in the water, you'll have water molecules swimming around, but you'll also have some other stuff, maybe salt or sugar. Are the sugar particles and the water particles, are they identical? No, they're not identical. So that's what makes it a mixture. So in our mixtures, we have two or more different particles. I should say types of particles, but that's fine. So you're going to need a little bit more space here, okay? So we're going to break up the pure substances. We're going to break them up into what? What two things? Elements and compounds. Elements are things that only have one type of atom. That's it. They're all made up of one type of atom. They're pure, and they're only made up of one thing off of the periodic table. So let's think about this. Oxygen, is oxygen an element?
Yes.
Yep. Sulfur, is sulfur an element? Yep. Iron, is iron an element? Yep. Helium, is helium an element? Yep. You see where I'm going with this? Okay. But let's take a look at some compounds. Compounds are still pure substances, but they've got two or more elements that are bonded together. And so, what's a really common compound?
Water.
H2O. Sodium chloride's another one. Sodium chloride, here's my model of sodium chloride. Do you see how there's a sodium here and a chloride here? So that's like a unit of sodium chloride, these two things. Do you see any other units of sodium chloride? Right here. There's a unit of sodium chloride here, and another here. You know what I mean? And another here, and another here, and another here, and another here. Right? But they're all, it's all made up of the same types of units, right? Sodium chloride, sodium chloride, sodium chloride, sodium chloride. So this thing is a compound, and it is pure. What else? Any other substance? Sodium bicarbonate. What? Methane, good. Yeah, we're done here. All right. Let's split mixtures up into two different things. What are the two different things we're going to split mixtures up into? Good. Homogeneous and heterogeneous. What is the prefix, like the word that's attached to another word? What does the prefix homo mean? The same. It means the same. What does the prefix hetero mean? Different. Or yeah, I'm not a dictionary, but those are the words that I've used to describe them. The same and different. So we can use the word homogeneous. Another way of saying homogeneous is homogeneous. And then we've got heterogeneous. I'm not going to call homogeneous that often. I'm really not going to call it a homogeneous mixture. I'm going to call it a lot a solution. And this whole unit is on solutions. It's how we can kind of define some things. What are some characteristics about this solution or that solution, blah, blah, blah. Okay, so what are some solutions? What makes the difference between homogeneous and heterogeneous?
Homogeneous is everything the same.
Homogeneous is where it looks like everything is the same, right? Yeah, absolutely. So when's the last time you made Kool-Aid? No? When's the last time you made iced tea?
No, never.
No. Oh my God. When's the last time you let like 7-Up sit out on the counter for like 5 hours and all the fizziness went away? Oh my goodness. Okay. Ugh. Salt water. Can you see, when you look at a little bit of salt water, can you see the salt in the water? Yeah. No, you can't. Wim, have we had this conversation before? I don't know. I can't remember if we had this conversation last year. So a homogeneous mixture is something where it looks like it's all the same, but you know it's not. You know it's made out of different particles. So a mixture of H2O and NaCl. Or a mixture, yeah. Would milk be one?
Yes.
No.
Chunky milk.
No. Well, okay. Chunky milk is for sure a heterogeneous mixture, right? So, and just by saying those words, thank you for the picture, John. I really appreciate it, okay? But for sure, chunky milk. Do you know what chunky milk is? Spoiled milk, right? Gross, disgusting, spoiled milk. Okay? But what about milk? What about just regular everyday milk? Is milk going to go under the homogeneous or the heterogeneous?
Colloid.
What?
Colloid.
It's a colloid, and a colloidal mixture is heterogeneous.
I didn't know it was a colloid.
Just regular everyday milk is a heterogeneous mixture. And now, I agree with you, Jenna. When I look at milk, it sure looks like it's all one uniform thing, right? Okay, but what do you know is, what's the biggest thing that makes up milk? What's the one biggest thing that makes up, if you were to pour a glass of milk, 90% of it is?
Lactose.
Water.
Oh.
Right? It's water. It's a bunch of stuff dissolved in water. So what does water normally look like?
White. I mean.
It's not white. It's transparent and it's clear, right? So milk, does milk look like water? No. There must be something in the water that's blocking light from getting through, right? And so that's what I mean. It's a heterogeneous mixture because you know it's mostly water. We now know it's mostly water. You know it's mostly water, but there must be something else. There must be some other type of particle that's blocking the light from getting through the water. Using that definition, can you tell that there's more than one type of particle? Yeah, because if it was just water, you'd be able to see through it, right? Okay. Now I don't want you to confuse that with like when I put blue food coloring in water, that's homogeneous still. It's absorbing different colors of light, but it's still letting the light through, okay? So like blue food coloring in water is homogeneous. It does all look like one thing. Heterogeneous, the only reason why milk is under there is because it's physically redirecting the light. Okay? So it's interacting with the light in some way. Tommy. Yes, for the most part it has to be clear. Unless the substance that you dissolved the substance in to begin with wasn't clear to begin with. For example, iron. Can you look through a sample of iron? No. But I can make an alloy of iron and carbon together. It's called steel. Okay? Now the iron wasn't clear to begin with, and the steel isn't clear. But that's still a solution. Does that make sense? Yeah, it's only because we deal with water most of the time that we're worried about it. Okay, what are some other solutions? Yeah, let's talk. We'll talk about it in a second. Is that okay? We'll talk about it later. So water and salt, water and sugar, anything dissolved in water, basically. As long as it's totally dissolved, it's a solution. So let's try this. Elements. Elements are pure substances that are only made from one type of atom. So let's talk about oxygen gas, okay? Let's talk about oxygen gas. Let's draw a picture of oxygen gas. What's the formula for oxygen? O2. Do you agree this is kind of what an oxygen molecule would look like?
Yes.
Two oxygens bonded together. And so now, if you had a bunch of oxygens, if you had pure oxygen, this is what it would look like. Do you get my drift? Are all of these particles, this is here, this is a molecule of oxygen. Are all of the particles totally identical? Yes, they're all totally identical, so it's pure. Good. Moving on. Compounds are pure substances that are compounds. Sorry. They're substances that are made of two or more types of atoms bonded together. So let's talk about H2O. Here we've got an O bonded to two H's. They look like Mickey Mouse, but just on its head. Would you agree with me? Again, this is one molecule of water. Would you agree with me that all of the particles that are floating around in this water, they're all totally identical? Would you agree with me? Yeah, this H2O and that H2O and that H2O, they're all. So this is still pure. Do you see how both of these things are pure? You know, one's an element, one's a compound. I get that this is made of different things, but all the particles are still totally identical. And then when we look at mechanical mixtures or heterogeneous mixtures, that's like salt and pepper. That And so it's like clumps of these and clumps of those, okay? And so you can very easily discriminate between the two things. Salt and pepper, chunky milk, gravel, granola, concrete, cookies. What about a chunk of wood? What? Yeah, but what does a block of wood look like? If I had a block of wood, would you be able to see the grain running through the wood? Yeah, well then there's visual differences. That's heterogeneous, right? If, what? What? What is wood made out of? Wood is made out of lignin and carbohydrates and proteins and all sorts of stuff. Yeah. Wood's made out of wood. Okay, now let's talk about solutions. We're pretty much done that first part of your review booklet, like pretty much. We already finished number 1, which was can you discriminate between, homogeneous, heterogeneous elements and compounds. That's basically it. But now solutions are homogeneous mixtures. What does that mean? That means that it's something when I add it to something else that you cannot tell the difference. And so here I should really be wearing proper protective equipment, but that's fine. Can you tell the difference between these two things? Yes? No? Maybe so? What? Well, yeah, okay. Okay. One's shorter and one's bigger. So here I've got a beaker that contains something, and here I've got another beaker that contains something. I want to tell you right now, one of these contains water, which is a pure substance, and one of these contains a solution of really concentrated hydrochloric acid. Okay? What? No. So the water, no. The water's here, the hydrochloric acid is here. Can you tell the difference between the two just by looking at them? The one on the left looks a little bit more clear. The one on your left. This one looks a little bit more clear. Kylan, you're crazy.
Wait, I would drink both of them.
What? What?
They look nice.
Okay. So when I add the hydrochloric acid to the water, okay, again, you don't really see much of anything.
There's bubbles.
There's not bubbles.
Wait, are there?
There's a difference in density, so one sinks way down to the bottom and the other stays on top. Okay? So when I look at this, I don't know how much you can see here. I'll put it in front of this thing, hopefully that you can see that. When I add this hydrochloric acid, I don't know if you can see it pooling at the bottom. Yeah, and that's because one of these has a different density than the other, that's all. But does it look like, can you tell the difference now that I've added the hydrochloric acid? Can you tell that I've added the hydrochloric acid? Or does it still look like water? Yeah, so that's the difference. That's what a solution is. A solution is you can't discriminate between the particles in that mixture. Okay, there is always a solute and there is always a solvent. So what I was doing there, what was I dissolving in what? I had hydrochloric acid and I had water. Which one was the solute and which one was the solvent? Do you remember? The solute is the substance being dissolved it's usually the amount, the one that's in less amount. Do you know what I mean by that? Like in that, I had a lot of water and a little bit of hydrochloric acid. The solute is always the one that's the smaller amount, right? So I dissolved the hydrochloric acid into the water. So as an example, we could say salt being dissolved in water, or hydrochloric acid being dissolved in water. The solvent is the substance. Well, if it's not the one being dissolved, what is it doing? It's the one doing the dissolving. Doing the dissolving. Which is such a stupid way to phrase that sentence. But hopefully you understand that that's a very clear way to get the idea across. The substance doing the dissolving. By way of an example, water. Water is not the only solvent, but it's the most common solvent. It's the one solvent we use the most because it's the most common thing on the planet, basically. Solutes and solvents may be gases, liquids, or solids. Okay, so an example, what did I just mix together? Water and hydrochloric acid, right? Now, I want to be very clear about that. Hydrochloric acid started out originally as a gas, okay, but that's fine. So hydrochloric acid into water. Water is a liquid. The hydrochloric acid used to be a gas. It used to be a gas. It's not anymore. I mean, you saw me pour it. It's not anymore, but it used to be. What? I dissolved it in water. Yeah, hydrochloric acid used to be a gas, and then I dissolved it in water, and then I poured the solution of hydrochloric acid in water into more water.
What's the percentage?
I'm not going to tell you what the percentage is. Really high. That's really super concentrated acid. Anyways, another example. Could you dissolve any solids into liquids?
Yeah.
Yeah. Salt into water, sugar into water. Sugar is a solid, water is a liquid. Okay, what else? Could I dissolve other liquids into liquids? Yeah. Have you ever bought hydrogen peroxide or used hydrogen peroxide ever in your life?
What is that?
You don't know what hydrogen peroxide is?
No, like rubbing alcohol.
Yeah, it's kind of like rubbing alcohol, except it's a little bit different. It's still a disinfectant.
Oh, yeah.
It still cleans wounds, right? So H2O2 into H2O. So right there, we've got three examples. We've got a gas dissolved in a liquid, a solid dissolved into a liquid, and a liquid dissolved into a liquid. Okay. Does the solvent always have to be a liquid? No. When? Question. Pardon? Yeah, iron and carbon, not carbonate, right? Yeah, iron and carbon. That's going to make an alloy. Iron is a solid, carbon's a solid, but when we heat them up so that they're liquids and we mix them together, then we can make steel, which is an alloy, right? What's another one? What's surrounding you right now? It's hitting you in the face.
Empty.
Air is, right? Air is a solution. Can you, when you look through the air, right here, right now, can you tell the differences in all the particles surrounding you? No. What gases are surrounding you right now?
I can smoke.
Yeah. So it's oxygen gas dissolved into nitrogen gas. Which one of these is the solute and which one of these is the solvent? If I said nitrogen gas was 78% of our air and oxygen gas was about 20% of our air, which one to you is the solvent and which one is the solute? This is the solvent, right? And this one is the solute. Hopefully that makes sense. Yeah. Not that big of a deal. Any questions on that? No? Okay, we're gonna mosey, we're just gonna scooch, we're gonna go real fast, okay? Solubility. Do you remember using this table last year?
Yes.
Oh, you better. Goodness gracious. I'm gonna write out some compounds and I wanna make sure that we know how to use this table, okay? Sodium phosphate There we go. So I've got 4 compounds listed on here. I want you to tell me, are they very soluble in water or are they only a little bit soluble in water? Keep in mind, if they're very soluble, what do we write in the brackets? AQ for aqueous. If it's only slightly soluble, how do we write that? Solid. What's happening here is when I add some ionic compounds, they will mostly break up, or all of it will break up. When I add some ionic compounds, they will only a little bit break up, okay? Do you want me to run through the very first one with you as a recap of how to do this? Yeah, I think we should, okay? Sodium phosphate, is this an ionic compound?
Yes.
Yes, I should hear a chorus of yeses coming at me. Why? Because we spent almost a week at the beginning of the semester trying to figure out if things were ionic or molecular, right? This is ionic. So it's made out of positive and negative ions. What's the positive ion? Sodium, and what's the negative ion? Phosphate. PO4 3 minus, right? Let's start always at the top of this chart. Always we're starting at the top. And let's go through this. And let's try and see, what do you notice about the vast majority of these ions at the top? They're all negative charge except for ammonium, which is NH4, right? Okay, so what do you want to do? What do you want to start with? The positive or the negative ion? The negative ion. So let's find PO4 3 minus, right? PO4 3 minus is right here. That means all of our attention is concentrated in this column, right? We're not, just because I find something over here doesn't mean it has anything to do with phosphate. Phosphate is only here. So, let's see. Phosphate is partnered up with sodium. Where do you see sodium in here? It's mostly or very soluble, and it's a group 1 ion. Well, how do we know that sodium is a group 1 ion? Because it's in group 1 of the periodic table, right? So because it's in group 1, we call it a group 1 ion. So is this combination of a group 1 ion and phosphate, is it going to be very soluble or only slightly soluble? Very soluble. I will put the letters AQ at the end, telling you that. Okay, let's do the next one. So I'm going to erase this. Let's do the next one together. No, you do it. You do it. You 3. Just do those 3.
Mister,
Yeah.
could I go to the cafeteria and buy something, please?
Yeah, okay. Yeah. Done? Wrong. And I'm not going to tell you which one is wrong. Got it? How can I check? If you don't write it down.
I don't know what I mean.
Okay. What? Wrong.
That's correct.
There are 2 wrong things in there. One of them is right and 2 of them are wrong. Okay? Yeah.
Why is there a PBI?
No, one of them is wrong.
PBI too. Oh, different charges.
One of them. I mean, those ones you did so far.
I see. Straight question.
You have no idea. Okay, well, let's split this up.
This is PB2 plus.
I.
PB2 plus ammonia. So aqueous and ionic. I don't know.
Do you see what the hell is this?
Yeah, this is aqueous. Find it.
Yeah, that what?
The A.
What is carbon dioxide? Carbon dioxide. What is
It's gotta be, right? If there's four negatives, so it's gotta be
So
four
what is
positives, right?
right?
what? It's PB with a 2 charge, 2 plus.
Correct.
I see.
Wrong.
Wait.
What? Okay, what do you start with negative, right? Okay, what is I? Okay, what's P? Yeah. What is P? No, I need to lead. Hey, which lead is this? Let's multi-valent. Which lead is that? Start on. Let's start on one.
This is way better than TST. No.
Yes. Hey, I'm intentionally being a jerk, aren't I? Yes, I'm intentionally being a little bit of an a-hole.
Maybe.
Maybe. What do you mean maybe? Okay, let's figure this out. What's I? Iodide. It's the element iodine, but it's. Do we agree this is an I minus ion? Yes. Okay. So what does that mean? The PB has to be PB 4 plus, right? Are we okay with that?
Yes.
It has to be lead 4 plus because there's 4 iodides. So let's look for the combination of iodide and lead 4. I see iodide here. Do you see lead 4 down here? No, so it's very soluble. Right? Do you see lead down here?
No.
I see lead 2 plus,
But not 4.
not 4 plus. So lead 2 plus will be not soluble or slightly soluble. So we're going to put a solid on lead 2, but on lead 4 we're going to put aqueous. Does that make sense? Oh, there's a world of difference between lead 4 and lead 2. There's a mountain, there's an entire, there's miles of difference between those two things. So we have to be able to spot them from a mile away. Calcium carbonate. That one's easy, right?
Solid.
Yeah, carbonate, not in here, must be in here, solid. That is such an underdeveloped skill at the grade 10 level. Holy guacamole, we need that so bad. Toka, question? No, okay, you're just hanging out. Okay, so let's talk about our last section in here. Our last section is the properties of aqueous solutions, and we're going to go through this pretty quick. Okay? There are 2 properties of aqueous solutions that are very easy to test for in the lab. They're called diagnostic tests. Whenever I say describe for me a diagnostic test, that means tell me what you would do in the lab. Step 1, dissolve the thing in the water. Step 2, perform a conductivity test. That kind of thing. Okay? Solutions that contain ions will be able to conduct electricity. What's an ion? Wim? It's a charged particle, right? An ion is something that has a charge on it. So ions will be able to conduct electricity. We call these solutions that can conduct electricity, we call them Are electrolytes important?
Yes.
Yeah, big time. Any sports people who talk about electrolytes often? Yes. Electrolytes. Electrolytes are super important because electrolytes are the reason why you can conduct electricity through your nerves. Okay, solutions that have no ions cannot conduct electricity. Solutions that have 0 ions cannot conduct electricity. We call these solutions, if it's not conductive, what are we going to call it?
Non-electrolyte.
A non-electrolyte. Which of these solutions contains ions? Let's think about this. Sodium chloride, is it ionic? Okay, then it contains ions, right? So is it going to be conductive? Yes. Good, lovely. Hydrogen chloride, is it ionic?
No.
No. But what is it?
It's positive.
Is she? It's an acid, right? And do you remember what the really important thing about acids is from Science 10? They make, this thing will eventually make a hydrogen ion. If it makes hydrogen ions, does it contain ions? Yes, and if it contains ions, is it conductive? So all acids are conductive. That's what I need you to understand. All acids are conductive. Okay, next one. Potassium hydroxide. Is it ionic? There should be a chorus of either yeses or nos coming out at me. Do you understand? The difference, spotting an ionic and a molecular compound is such a pivotal, crucial skill that if we don't have it by now, we need it for Monday. Okay? Is this an ionic compound? Yes or no?
Yes.
Why is it yes, an ionic compound? It starts with a metal, end of story. Right? It's a metal, non-metal combination. That means it's ionic. Yes. What about the next one? No. This is what we call a molecular compound, and it's not an acid, right? So this will not be conductive. It's the only one on there that's not going to be conductive. CHL, what? HCl? HCl? Why is this an acid? How can you tell that it's an acid? Oh, acids are either H something or they end in COOH. Yeah. So those are acids, right? Yeah. As long as we're comfortable with that. Okay. Sodium chloride. This has ions in it, right? So it's conductive. Acids make ions, so they're conductive. This thing, this is actually a base. You don't want to be on camera? Hi. I'm going to blur her face. I'm just kidding. I can't edit it. I have no idea what I'm doing. Okay. Potassium hydroxide. This is actually a base, right? But all bases, as far as you're concerned right now, all bases are ionic compounds, so it doesn't matter. It's ionic. And then this is the only one that's molecular, okay? So that's a conductivity test. And I want to prove to you, do you remember what I added to this thing earlier? What did I add to it?
Acid.
Hydrochloric acid. So I'm going to add the rest of the acid, okay? So it's quite acidic. It's super acidic. It's very acidic. It's concentrated acidic. Okay? And I want to prove to you that this thing is, yes, it's conductive. Thank you. This thing is a conductivity tester, and I'm going to prove to you, does water conduct electricity?
No. No.
Yes.
No.
Does pure water conduct electricity?
No.
Oh man! Does pure water contain ions? Is pure water an ionic compound? H2O, right? No. Okay, now here's the deal. Is pure water an acid? I get that it starts with H something. But is pure water, are you showering in acid every day? No, okay? Just use some common sense. So water is not an acid and it's not ionic. So that means it's molecular, right? So is it going to be conductive? And let's prove to you that it's not conductive, okay? So let's prove to you that it's not conductive. Let's take our conductivity tester. Okay? Let's take this, and I'm going to put this, and if the light bulb goes off, it's conductive, right? 3, 2, 1. Is it conductive? Womp womp. Okay? So water, pure water is not conductive. Now I'm lying to you. Everything is a little bit conductive. Everything conducts like a little bit. Do you know what I mean? You can never permanently stop the flow of electrons through something. Everything is a little bit conductive. So let's try that acid. I added the acid to water. What do you think? Is this thing going to be conductive?
Yes.
It should be, and if it's not, I'm in for a world of hurt, aren't I? Let's try this. 3, 2, 1. No way. No way. You see that? That's awesome. Okay, I'm going to unplug this before I electrocute somebody. Okay, we good with that? Yeah? I don't know how to edit video, so I'm literally just moving the camera, and this whole thing is going to go onto YouTube. And that's the worst. Yeah, your face is going to be on YouTube.
Nice.
Okay, let's do conduct. Let's talk the litmus test. What?
I didn't find this paper.
It's not in the bin?
No, I didn't.
It's in the bin. Did I not put it in the bin? You saw me put it in the bin. It's in the bin, right? Yeah, it's in the bin. I'm not crazy. You're crazy. I'm not. Okay, litmus test. A litmus test is an indicator. Yeah. Is there a review booklet and 5.1? Is there anything that says 5.1 in there?
Yeah.
Yeah, okay, there we go. It's an indicator to tell if a sample is acidic, neutral, or basic. Okay, acids turn litmus, what do you remember?
Red.
Red, right? Yeah. And bases. Right, so acids turn litmus red. Doesn't matter what color it started as, it's going to turn red. Bases turn litmus blue. Doesn't matter what color it started as, they turn it blue. And neutral substances what? They don't change. We only have 2 types of litmus, and I'll give you a hint, they're the exact same thing, okay? There's red litmus and blue litmus. It's the exact same chemical. It's just that one we treated with an acid before we dried the paper and cut it up. One we treated with a base, and then we dried it up and we cut it up and stuff. So litmus is just litmus. Red litmus and blue litmus is the same thing. Okay? It just depends on if something is acidic or basic enough to change its color. Neutral substances don't change litmus at all. Acids always begin with or end with. Bases are always, I need you to pay attention to this. Bases are always group 1 or 2 hydroxides. What does hydroxide look like? What does hydroxide look like? It's OH minus. Good. It's OH minus. So what does that mean? That means that hydroxide has to pair up with positive ions, right? It has to be ionic. It has to be ionic. A group 1 or a group 2. Now, what are all the group 1 positive ions? This. Lithium, sodium, potassium, rubidium, cesium, francium doesn't exist. You'll never see it. Don't worry about it. Okay. Then what's group 2? Beryllium, magnesium, calcium, strontium, barium, and radium doesn't exist. So you'll never see it. Don't worry about it. So, let's think about this. Whenever you partner up hydroxide with any of those group 1 or group 2 things, that's what we call a base. Okay, it's always a group 1 or a group 2 hydroxide. So let's look through here. Let's label these three things. They're the same 3 that we did on the last slide. They're the exact same things. Is NaCl, is it neutral, acidic, or basic? Is it acidic? Does it begin with an H or end with COOH? No, so it's not an acid. Is it basic?
Isn't it neutral? Yes, neutral.
Is it basic? It's not basic.
Oh no.
Is it a group 1
Yeah.
hydroxide? No. It has to be both of those things, right? A group 1 or 2 and hydroxide. So what is it, Luke? It's neutral. And we're going to call it, this is neutral ionic, okay? Because we're going to discriminate between ionic and molecular. Okay, what about the next one? Acid. Hopefully you can spot HCl a mile away as an acid. Is that okay? What about the next one?
Base. Has no base.
Is it a group 1 or 2? Yes, group 1 hydroxide. Yes. And then the next one. It's not an acid, it's not a base, so it's neutral. And we're going to say that it's neutral. Neutral molecular. Hopefully you're okay with that. So let's figure some stuff out, okay? Let's be really, really clear about this. Man, we don't have a lot of time to write that lab thing. Holy. Okay, we don't have 5 minutes. We have 7 minutes.
Okay.
We don't have 5 minutes. We have 7 minutes. Yeah, I know. Calm down. I know. Okay, let's take a look at this. I'm going to add some distilled water. Sodium chloride, would you agree that's regular table salt? Yeah. So is water conductive? No. Now that I add salt, is it going to be conductive? Yes. Okay, let's try this out. I'm going to add the salt. I'm going to try not to kill myself. Here we go. Ready? 3, 2, 1, flat. Ooh, a little bit. And as I dissolve more and more salt, what happens to the conductivity? It gets brighter and brighter and brighter and brighter and brighter. Now, let's take a look at it. Let's take a look at it and see. Sodium chloride, the sodium chloride in water, is it neutral, acidic, or basic?
Neutral.
It's neutral, so what should red pH paper do?
Nothing. Wow.
Did the red turn blue? That's the only other option. Did it turn blue?
No.
No. Okay. Let's try the blue. Did the blue turn red? We'll see.
No.
Did the blue turn blue? Sorry, red. Did the blue turn red? No, so red stayed red and blue stayed blue. Is it ionic, is it neutral, acidic, or basic? It's neutral. Okay, good. Let's take the next thing. What's the next thing on our list?
HCl.
HCl. Let's take that really concentrated HCl that I was talking about earlier. We already saw that it was conductive, right? So let's try a red and blue litmus paper test on it. Let's try red. Did the red change color? No, the only other option is blue, right? So, no. Okay. Did the blue change color?
Yes.
Did the blue change color?
Yes.
Yes, 100%. It turned, the only other option is red, right? Nobody needs to say salmon or something. It didn't turn salmon colored. It turned red. I know it's not red, but it turned red. Okay, good. Nice talk. Anyways, next. What's the next thing on there? Okay, is it okay if I substitute KOH with sodium hydroxide? No. Well, too bad. I don't know what to tell you. Okay, let's try this. I'm going to dump a bunch of sodium hydroxide into... I'm going to put it in water because it's way too concentrated right now for me to handle safely with proper safety equipment. So I'm going to put a buttload of the sodium hydroxide in here. Okay?
What happens if you put your finger in?
If I put my finger in what? Here or there? Here. Both. This one slowly after several minutes would start to give me like first degree, then second degree, then third degree chemical burns. Here it would be even slower, but it would still happen. It would slowly, even slowlier give me that. Okay, sodium hydroxide, is it supposed to conduct electricity? Is it supposed, are bases supposed to conduct electricity?
Yes.
No.
KOH, is KOH supposed to conduct electricity? Is it ionic? Yes. Is it supposed to conduct electricity? Yes. Good. Okay, now let's do our litmus paper test, and then that's going to be the last thing we're going to do. We're not going to be able to write any notes, we're not going to be able to write any lab reports today or lab procedures. That still doesn't mean you can just pack up right now. We're not done. There's 2 minutes left? Yeah, I shouldn't have said anything, should I? No, I should have not. You're not paying attention at all now. Nobody's paying attention at all. That's me sarcastically telling you to pay attention. Okay, sodium hydroxide, potassium hydroxide, kind of the same thing. Are we okay with that? It's a group 1 hydroxide. Okay, it was conductive, just like we half predicted. Most of us predicted it. Blue litmus paper. Did any change to the blue litmus paper? No, because it's maybe Did it change blue? Yeah, some people are going to call this like violet or something, even though it's not close to violet. Some people are going to call this some weird purple color, okay? What's your only 2 options for litmus paper? Red and blue, all right? And we already saw that neutral molecular compounds don't conduct electricity and they don't change litmus paper, okay? Wim.
Why did we bring our textbook?
Because you need your textbook for Monday. That's why you brought it today. Because we were going to get to something, but we just too late. Or I was just too slow.